Alright, so for 4.1, your essential questions are, in words, how do you integrate with powers? And then your second one, how do you solve a differential equation of the form f double prime of x equals, and it could be any formula that they give you. If you have an easier time using a specific one, you could make up a specific formula and then go through the steps and like write out the steps of what you're doing. So in words, how do you integrate with powers? You'll learn that today. And then how do you solve a differential equation? We will do both ones that have f prime and f double prime, but if you can answer how it works for f double prime, you'll be good to go for the others. Objectives, you're going to learn how to integrate with powers, you're going to learn how to integrate e to the x, and you're going to learn how to integrate trig functions. Integrating is just taking the integral, and again, the integral is what we've been finding, that stretched out s part. First day, we approximated integrals with rectangles and trapezoids. They were too big or too small. Second day, we found exact integrals if it was area. If we knew the exact area above or below the curve, we added the area above the curves and we subtracted the areas below the curves. And then today, you're also going to learn how to solve differential equations. So we talked briefly about this yesterday, making completely sure now that you pay really close attention to equations and questions and directions, that if they give you a capital F versus a lowercase f, that we can tell the difference of that in your writing and your explanations, because they're very likely to keep the same lettering and just make one uppercase and one lowercase. So definition of an antiderivative. So now we're moving into this whole idea that integrals undo derivatives. They're antiderivatives. So a function f, capital F, could be an antiderivative of little f if I differentiate capital F and get little f back out. So here's an example of a little f, 3x squared, and we thought through yesterday that possible antiderivatives would be x to the third or x to the third plus any constant. Well, they're going to say, okay, any constant, they're going to call that c, so we're going to say that x to the third plus c is an antiderivative of f, of little f. Excuse me, sorry. Alright, so what we mean by that is that if we're claiming that's an antiderivative, then we could say that capital F equals x to the third and capital F prime equals 3x squared. And so we've verified that capital F prime is equal to little f. It's not all the time that they're going to ask you to make those connections between the capital F and the little f, but if they tell you that capital F is an antiderivative of little f, that's what it means. You could differentiate capital F and get back to little f. So again, whenever we have this plus c part, that's when we're talking about what we call a general antiderivative. That means that there are no bounds, no number bounds on the top and bottom of the integral. It's just an integral itself. It also means this whole plus c idea, the constant c idea, means that antiderivatives come in families or groups. There are lots of different options that are okay. they're all just different from one another by a constant. So one time you might, for example, be adding like plus 5, another time subtracting 3 halves, something like that, but they all have the same base part in the sense that they start with x to the third. Okay, so representations of antiderivatives. If capital F is an antiderivative of little f, and then they're telling you capital G is an antiderivative of little f, so they're giving you two different options. So capital F is an antiderivative, capital G is an antiderivative, they both are. Well, then how are they connected? Well, this theorem tells you that those two are connected to one another in the sense that G is the exact same as F with the exception of a constant that you could add. Oops, sorry, that blended really terribly. Let me do like yellow. With the exception of a constant. The constant C is called the constant of integration. Okay, so what this tells us because of the plus C is that antiderivatives or integrals, or integrals are not unique, meaning there's not just one of them. They are not unique, but they are related. It's not just that there are tons and tons of crazy different options. It's that, but they only differ by a constant. So they're related to one another pretty closely. So this plus C family effect, by adding the plus C at the end all the time, you need to think back to what that does algebraically to your functions. So think back and connect to like algebra 2 math analysis. What's the difference between x cubed plus 1, x cubed minus 5? How do those change? What kinds of shifts are they? Well, they're vertical shifts. They move you up and down. So your base antiderivative would be where C equals 0. And then you would have all these other options where you're adding and subtracting different numbers. Okay, just so that you have all this terminology straight, so we've kind of introduced it in pieces, but so that you kind of have it now all in one spot. What is integration? So the term integration, that is the process of finding an antiderivative, and the process of finding an antiderivative can be called two different things: anti-differentiation or indefinite integration. They mean the same thing. Okay, the indefinite part. Indefinite just means that there are no bounds. So you're going to be looking at the integral of, say, f of x dx, but there are not going to be any numbers on the top and bottom like you've seen up until now. Some vocabulary, the differences between the verbs versus the nouns. So the verb would be the process piece. The process of finding that is anti-differentiation or indefinite integration, like we've talked about. The noun, what you end up with, is an antiderivative or an indefinite integral. You're taking a national test. Again, we never know what they're going to tell you vocab-wise, so you just have to be prepared to read everything. Alright, to read an integral out loud, here's how that would work. So you see the integral symbol here. So you would say the antiderivative or the integral of, well then they have to tell you what the function is. So of f, or f of x, and then they have to tell you with respect to what, that's the dx part. So like for derivatives, you used to say dy dx, and that part told you with respect to x. Now you have your integral part and then dx, and that means the same thing with respect to x. All right, continuing that a little bit further, you could extend that. You could talk about, for example, instead of a function f, maybe it's a function g. Instead of x, maybe it's g of a dA. Or some trig function, maybe it's like h of theta d theta. You could extend that whole idea of being with respect to anything, really. Okay, breaking down all of these pieces. So again, this funky looking stretched out S, that is an integral symbol. Then you have to have what you're taking the integral of, and the fancy term for that is an integrand. If you remember, the inside of a radical is really called a radicand, so the inside of an integral, an integrand. Then the dx part is the with respect to. And then you're given answers, this whole capital F of x plus c piece. And since we don't have any bounds and we're adding the c, this is the general antiderivative. Or the indefinite integral. Hold on for a second. Alright, sorry. Those of you, third block, who had been asking, the dog needed inside. Okay, next part. So we've gone over vocabulary. Now just some things to remember. We talked about this yesterday in class. Really connecting this idea that derivatives and integrals undo each other. So derivatives go one direction, integrals help you backtrack, go the other direction. Integration is the inverse of differentiation. Differentiation is the inverse of integration. So what that means, based on those being inverses, if I want to integrate a derivative, I should get back out the original. So if I integrate capital F prime, I should get out capital F with the plus c. And then if I want to differentiate an integral, they should wipe each other out, basically, and I should get what's on the inside there. In this case, since you are integrating and your derivative is inside, anytime you're taking the integral, you get the plus c. If you integrate first, you would already have the plus c, but so you'd be taking d dx of something that had a plus c, and since you're going to differentiate that plus c part, that's going to go to 0, and so you just are left with that inside piece, no plus c in that case. That's why it cancels out. Alright, one of your essential questions talked about this power rule idea. Let's try to break that down. So notice where things are going and kind of follow them through. So you start with x to the n that you're going to integrate, and they tell you that's x to the n plus 1 divided by n plus 1, and then plus c. So let's take an example. So like x to the 5th dx, if I want to integrate that, they're telling me I need to add 1 to the power, so x to the 6th, divide by the new power 6, and then plus c. Well, if you want to check, say that y is equal to x to the 6th over 6, and then find y prime. Well, y prime would equal 6 x to the 6. Sorry, I'm saying one thing and writing something else, and neither of them are correct. 6 x to the 5th, and then it would already be over 6. Those 6's cancel out. You get x to the 5th, which was what was inside right here. So it worked. So if you do want to check your answer, you could integrate, then take the response for what you got when you integrated without the plus c part. Take the derivative and verify that you get back to the inside of the integral. They're connected. You can keep looping from one to the next. Then there's this really important part here that says that n cannot equal -1. Well, why not? Let's take a look at what that would look like. So, for example, say I want to integrate x to the -1, and I want to use this power rule. So x to the -1 dx, that would be x. You would add 1 to the power, so you would get 0. X to the 0 is okay, that just equals 1. But then you would have to divide by 0, and that's not okay. So the n can't be -1, excuse me, because you can't divide by 0, and you would have to. So this ties back down here. That leads us to a very important, connection and idea. It's really important that n can't be -1 so that you recognize that, okay, x to the -1, that's really the same thing as 1 over x. That also carries through to anything else over x. 2 over x is not okay. Any constant over x is not okay at this point. We don't know a rule to integrate that. So the power rule works unless you have the -1 power, and then you have to do something else. We actually won't learn about that for a little bit. Okay. Some ways that might come across that are a little trickier could be, for example, maybe instead of just saying like 5 over x dx, which you should immediately recognize we don't know how to do yet, they might be a little more sneaky and say like 5x over x squared dx. But it turns out, if you slide down here for a minute, we have no product or quotient rule for integrating. So you just have to do some algebra to rewrite. And we have a sum or difference rule. So we know that if you want to add and subtract, you can do that a piece at a time when you're integrating. That's what you have to go back to. So since I don't have a quotient rule, yet they're giving me a problem with the quotient, I could say, oh, well, that's equivalent to, and then just do the algebra where those x's would cancel. So that'd be 5 over x dx, but I can't do that because it's a constant over x, and the power rule is not going to work. You should not run into that at this point in your homework, just simply because you don't have a rule for what to do next, but it is going to come up next chapter. Other things to remember, we reminded you of this in 4.2 and 4.3 day 2. You had all these properties, that constants can be pulled in front, that you can add and subtract your pieces. We didn't tell you there that there's no product or quotient rule, but now we are. There is no product rule, there is no quotient rule when you're integrating. Chapter 5, we will spend pretty much all of Chapter 5 dealing with e, the number e, like 2.72-ish, and then natural log, which is log base e. But for right now, it turns out rather uniquely that e to the x, that function, is its own derivative. So we can prove that later once we know a little bit more. But if you want to differentiate e to the x, you just get e to the x back out. Now, that could get a little more complicated with chain rule. So, for example, a chain example would be if instead of just regular e to the x, you had like y equals e to the 7x, then y prime would equal e to the 7x times 7. That 7 would not be an exponent, it would be down like in line with the e, but the chain rule would be taking the derivative of the power part. Otherwise, it's really simple. The derivative of e to the x stays e to the x. So then when you integrate e to the x, that's going to stay e to the x as well, e to the x plus c. Because derivatives and integrals undo each other. So the derivative goes like this direction, the integral goes back this direction. You get e to the x both times. That is more complicated if you had a 7x that you wanted to integrate with. You're going to have to wait till later this chapter before you know how to do that. So there is kind of a chain rule for integrals. But like I said, it will come later this chapter. So for right now, if you're thinking it's a chain rule sort of situation, you don't really know how to integrate that just yet. Okay. So we talked about you're going to have to know how to integrate with powers. We have that rule. Before we do problems, a bunch of trig integrals come up, so you need to know the different trig integrals. Well, that's connected to derivatives, so I reminded you of the derivatives. So this is how I had them listed for you back in chapter 2. And so I just relisted them again. Again, derivatives are going this direction. Integrals are just going to backtrack. So if derivatives go forwards, so in our little layout, derivatives are going this way, then integrals, since they're backtracking, are going to go this way. So the integral of cosine is sine. The integral of secant squared is tangent. The integral of secant tangent is secant. The integral of negative sine would be cosine. Negative cosecant squared would be cotangent. Negative cosecant cotangent would be cosecant. Now, oftentimes, instead of being asked to integrate negative sine of x dx and say, oh yeah, that was the answer I got when I started with cosine, they might ask you that, but they might also just say, I just want you to integrate sine of x, positive sine of x. How could you do that? Well, you could say that if I multiplied by a negative here to change this sign, I could multiply by a negative here to change that sign. And so the integral of sine of x is negative cosine of x plus c. So in the derivative case, if you were differentiating a co-function, then every single time you got a negative answer when you differentiated. Now it's going to turn out if you want to integrate, it's not when you integrate a co-function, it's when yeah, it still is. Sorry. It still is. When you're integrating a co-function, you get a negative back out, with the exception of this cosine piece. That's a little funky, but your lower parts work out that way. Still, that when you are integrating a cosecant or cosecant squared, you're getting a negative function back out. Okay. Next part, let's go ahead and mark this entire piece here, all 6 of these. You have to memorize this chapter. These other trig integrals, that would be that you have to memorize those in chapter 5. So for right now, if they come up, like they might come up in your homework, and I expect you to know, oh yeah, I have all of those, I know where they are, and just be able to go find it and use it. But I won't ask you that on a test for this chapter. Okay, give me 1 second. Okay, so we have all the rules we need. We're now ready to find indefinite integrals, or we're ready to integrate. Okay, we have no product rule, no quotient rule. The only rule you're working off of today is the power rule and trig. So I'm going to rewrite this as the integral of x to the 1/2 dx. For derivatives, you subtracted powers and they came in front. For integrals, you're going to add. So this needs to be x to the 1½ so 3/2. And then instead of multiplying in front, you're going to divide. So divide by 3/2, and then you're going to add c. Hopefully really quickly you're going to learn that, okay, if this is x to the 3/2 and I want to divide by 3/2, that's really the same thing as multiplying by 2/3, and you are more than welcome to skip from the original part to that step and be done. Okay, so you add to the power and you divide by the new power. All right. Next part, we are adding, and we said that that's okay. There is a rule that says we could really integrate 5x dx plus we could integrate 3 dx. You actually saw that a couple days ago. Okay, so the 5x dx, that 5 is a constant, so it's just going to hang out, and then you need to integrate the x part. So x, instead of to the 1, I need to add to it, x to the 2 over 2 plus c, and I'm going to put c1, c sub 1. Plus, and this 3 might be a little weird for you because there's no x there. So you might want to think about, okay, there is no x there. I could say it's x to the 0. So the 3 is a constant. And then how do I integrate x to the 0? Well, that would become x to the 1 over 1. And then I'm going to put plus c sub 2. Sometimes it's easier for people to think about, instead of the x to the 0 idea, they just think about, oh, this should become 3x, so that when I differentiate 3x, I get back to the regular plain 3. Some people just think that through, and that's totally fine. So we've ended up with 5/2 x squared plus c1 plus 3x plus c2. Then what we're going to do, those are both constants and we don't know what they are, but one constant, one number, plus another constant makes yet a third constant. So we're going to say to let c1 plus c2 just equal our capital C. So our answer is going to be 5/2 x squared plus 3x plus c. Now this is good for your notes so that you know why we did what we did. However, a couple of things to go back to. So since it's kind of your first time, you might want to check your answer. And if you wanted to check your answer, you would say, okay, assume that y equals 5/2 x squared plus 3x plus c. Now I want to find y prime. So it would be 5/2 times 2x plus 3 plus 0 for the c. Those 2's cancel, so I get 5x plus 3, which is good. That's what I started with over here. Okay, so that's one thing to kind of talk about and think about in your notes so that they're useful to you as you're working through. And then something else is that another option or a way that we would typically write it, we would typically just say, okay, the problem said 5x plus 3 quantity dx, that I want to integrate that. And I know that I can split this up because of this plus sign, but instead of actually showing the two integrals like we did, we could just do that in our heads and say, okay, here's the 5 part, the x becomes x squared over 2, plus the 3 becomes 3x, plus c. Okay, so 5/2 x squared plus 3x plus c, and I'm done. So it's totally okay to show it this way, where you don't necessarily write out all the steps. So for notes the first time, sometimes it's nice to see where everything comes from, but it is okay, instead of splitting it up into pieces, to just do the different pieces as you go, not write out all those different integrals. Okay, so no product rule, no quotient rule. We do have trig rules, but is there any function you can think of that would undo the cosine of theta over sine squared theta? Basically, like, is there anything you can think of that has this as a derivative? No, not of your basic 6 trig functions. None of my derivatives equaled that. So can we try to rewrite it? There are some different things that you could think about to rewrite it. One would be to remember that, like, sine squared of x plus cosine squared of x is 1. So one option would be to change this into cosine of theta over, for sine squared, 1 minus cosine squared of theta. But that still isn't anything that I know as far as a derivative answer. So while this is mathematically okay, it's not super helpful. Now, it wasn't helpful here. That's not to say it's not going to be helpful in some other problem. But if that wasn't super helpful here, then can we just try to rewrite? For example, like cosine theta over sine theta, and then just using algebra, that would be times 1 over sine theta that would be left, because when I multiply fractions, I multiply across the top and across the bottom. Well, that would turn it into cotangent of theta, and then 1 over sine is cosecant of theta. Is that something that was a derivative answer? If you think back through, yeah. If you had y equals cosecant of x, y prime was negative cosecant of x, cotangent of x. Well, I see the cotangent and the cosecant that's right here, but I don't see that negative. I would like to turn that negative into a positive. I could do that if I said instead that y should be negative cosecant. Then when I differentiate and I get a second negative, that would turn this into a positive, which is what I want. So that means this integral is equal to negative cosecant of theta plus c. You're trying to think about, when is this portion here, the integrand, when is it a derivative answer? Well, if I differentiate cosecant, I get negative cosecant cotangent, and you can always work with the plus and minus signs. That's not too bad. Okay, then for example 4, they're mixing them all together. So the 1/3 is a constant. It can just hang in front as I do my thing. And then we talked about you could write out the separate integrals, or you could just go through and do them as you're going through. So 1/3 times 2 is a constant. It would hang out there. And then the cosine, it always goes back and forth. Sine goes with cosine. I just write it down, and then I check my derivative. What is the derivative of sine? Okay, that's cosine. Good, I'm good to go. Plus the integral of e to the x is just e to the x. Plus, we talked about the integrals of constants. So up at the top of this page, we said the integral of 3 ended up being 3x. You needed to put the x back into the problem. So the integral of 1 is going to be 1x. And then plus c. I'm going to go ahead and call this C1, because what they do a lot of times is say, okay, this 1/3 would apply to everything, including that C1, and 1/3 times a constant is still a constant, so you're very likely to see it written 1/3 times 2 sine x plus e to the x plus x, close the bracket, and then just do a regular plus c out at the end. And what would really be happening is that 1/3 of C1 is equal to that regular C. They don't always come out and write this step that it's equivalent. Sometimes they just go to that for the answer, and that's totally fine. Okay, so there was some practice using the different rules. We've got one more with some trig before we look at a separate idea. So this one, we have parentheses within our integrand. We have a 2 as a constant out in front. You need to take a look and see, but we don't have a product rule. So let's go ahead and distribute so I can see my different pieces. So 2 times the integral of tangent of x plus tangent of x secant of x, parentheses around all that, dx. All of it is integrated with respect to x. Well, you should, just from knowing derivative rules, recognize that when you differentiate secant of x, you get secant x tangent x. So the integral of secant x tangent x is just secant x. But then you come over to this tangent x and try to figure out if that's any derivative answer, and it's not. So that's one that is just given a couple pages back. If you go back and look, the integral of tangent of x is negative natural log absolute value of cosine of x. I do not expect you to know why that works right now. I just want you to know that it is possible to integrate all 6 of the trig functions, even if it's not a derivative that you already know about. Okay, and we have our 2 that was hanging out in front of all of that. And then, like we talked about last time, normally they'll just put the plus c out at the end of that. It's totally fine if you want to leave your answer right there. It's also possible that they might say that that's negative 2 natural log absolute value cosine x minus 2 secant x plus c. That's all right as well. Okay. All right. Now we're going to get into this idea working with what we call differential equations. They just don't come right out and say it right now. So what they start off with is this idea about a ball being thrown upward, and they give you initial velocity 64 feet per second, and then they give you initial height of 80 feet, and they want the position function. And when they say derive the position function, they're not meaning to differentiate, they're meaning to develop the position function. Start with, in this case, they say beginning with the fact that negative 32 feet per second is acceleration due to gravity. So they want you to start with the fact that acceleration, a of t, is equal to negative 32. And let's go ahead and see where those units come into play. So that would be feet per second squared. Okay, they want you to use that and backtrack to get the position function. So derive in the sense of develop the position function, starting with acceleration and this idea about initial velocity and initial height. Well, we've now seen that integrals undo derivatives for us, and we already know that we start with position s, and then we differentiate to get s prime, which would be velocity, s prime. And then we know that we differentiate velocity to get to acceleration. So now that we know about integrals, if I want to backtrack, if I integrate acceleration, I should get to velocity. If I integrate velocity, I should get to position. So let's start with that. So if I want to integrate acceleration, I could then say that velocity, v of t, is going to equal the integral of negative 32 dt with respect to time. Okay, we integrate negative 32 by putting back in the variable. So instead of negative 32x, it'll be negative 32t, and then plus c. And this is what we would call, if you put the v of t back in there, this is what we would say is the general velocity equation. but you're able to figure out specific information because they tell you that you have an initial velocity. Back up in the problem, initial velocity was 64 feet per second. Well, what that means is that when t equals 0, v equals 64. So I could come back over here and plug in 64 for velocity, negative 32 times 0 for t, and I could figure out what c is. Instead of having a general formula where I could have any constant, I can figure out exactly what the constant is. It should be 64 when I zero out that other side. So then I can come back and say that velocity, v of t, is really negative 32t plus 64, and this is what we call a particular velocity equation. We were able to figure out what the plus c was. Well then, and you might want to note the units, so a of t was in feet per second squared. We're backtracking, so v of t is in feet per second. If I integrate and backtrack again, I could get to position. I think I had red going for position, yeah. So s of t is going to be the integral of the quantity negative 32t plus 64 dt. And so when I integrate that, I get negative 32. I've got to add to the power, so t squared, divide by the new power, so divide by 2, plus 64. I've got to put the t back in, and then plus c. And if you put the s of t on the other side, this is what we would call the general position equation. But if you go back up, they tell you that we had an initial height of 80 feet. What that means is that when t equals 0, s is equal to 80. So if you go plug that in, 80 for position, let's go ahead and reduce down the negative 32 over 2 would be negative 16. So negative 16 times 0 squared plus 64 times 0 plus c. So that right side zeroes out again except for the c's. So 80 equals c. And then you could go back and say that s of t equals negative 16t squared plus 64t plus 80. And those units would be, instead of feet per second squared, then we backtrack to feet per second. These would be just in terms of feet. And this is what we call the particular position equation. If you look really closely here, this is negative 16t squared plus v sub 0t plus s sub 0. And we've had you memorize this formula up until now. But now you've proven or derived the formula. You know where it comes from. It just comes from starting with your acceleration constant and integrating a couple of times, and that's why that works out the same every single time. Okay, we want to tie into this whole idea of general versus particular a little bit more. So particular just means that you have figured out what the plus c is. General is when the plus c is in the problem. Particular is when you can solve for the plus c and you know what it is. And again, general is when you keep the plus c. doesn't really matter whether it's position, velocity, acceleration, just the idea that if it's a general solution, it's going to have the plus c in it, and if it's a particular solution, it's going to be specific. You're going to know what the c is. So last idea is this part about differential equations. And you just have a handout because they could do this in so many different ways. We don't have time to work the same problem 6 different times. But they could use all these different notations for derivatives. We could use dy dx notation. We could use y prime notation. Or instead of y prime, we could say it's f prime of x. You never know what you're going to get. You have to be able to work with any of them. But the idea of solving a differential equation is that you have to find the original function when the derivative is given. So they start off giving you the derivative. Your goal is to find the original function. At first, it's going to involve this plus c. So the general solution is going to keep the plus c in the problem. Then we're going to do all this same work down here at the bottom to figure out a particular solution. And that's where you're going to find the plus c. Find a specific value for c. Let's start with general first. So we have all these different representations for the derivative, and you're trying to find the original function. They've shown a bunch of steps here. So this first step, they were taking and multiplying both sides by dx. And I'm going to switch colors. Multiplying here by dx, multiplying here by dx, to get what we call differential form, and that was from like 3.9 when you did linear approximations and differentials. Okay, it's also what we call separating variables. You have to be good at this. We're going to do a ton of differential equations, and if you only take the A-B test, you are super likely to see a differential equation in the free response section. Our kids are usually really good at them. They're pretty easy by the time we do a ton of them. Then we say, okay, we now want to figure out, instead of what dy is, we want regular y. So we're going to integrate, we're going to integrate, we're going to undo that derivative part and just get y. Because the reason that works out, if you want to integrate 1 dy, if you integrate 1 dx, you get x back out. 1 dy, you get y back out. Okay? Technically, you would end up with y plus c, but you lump all of your plus c's together, usually, for how that works out. I'm trying to think of where I want to squeeze that in so that you can see it. I think I have enough room right here. So it would be like y plus c1, and then that would equal, when you integrate again, the x to the third over 3 plus x plus c2. And then you could just lump these together and say that this capital C is equal to c2 minus c1. Just moving those constants around. Usually we just lump it together and go through. Like we would just go from this step to this step, and we would say, oh yeah, there really should have been a plus c over here with this y, but I know it'll work itself out by just doing the plus c on the right side, and that's totally fine. So if we start with the y prime notation, you can then say, all right, I want to integrate both sides. So I want to integrate this side dy with respect to y. I want to integrate this side dx with respect to x. Integral of y prime is y. And then when I integrate this side, I get the x to the third plus x plus c. And then same idea, if I have f prime and I want to figure out what f is, so I want to integrate on this left side with respect to x, integrate on this right side with respect to x, and then keep going. So they're representations of just all the different notations for derivatives, but you're really doing the same thing. If you're at a derivative and you want the original, you just need to integrate and add the plus c when you're done. Okay, so those are general antiderivatives. Excuse me. You guys are more than welcome to skip a few of those steps. Like a lot of times, let me pick a color. Maybe I'll just highlight. Let's highlight like in this. The purple wipes everything out. And we've already got green and blue. Yeah. So this step here is skipped a lot. I didn't mean that. It's this step on this one and then that same step on these others. The part where you're showing that you're integrating both sides. That's skipped fairly often. And it's also okay to skip this part about all the C's and just add your C over on the right side. Okay, the only change when we leave it with the plus C, that's what we call the general solution. Then you have to have what we call an initial condition to get a particular solution. And the particular solution is when you're going to find what C is. The initial condition is that you're given a point to work with. And then you plug that point in to figure out what C is. So let me find a pen so that we can draw our little divider, because from this step over, this is the same as above. So if you want a general solution or a particular solution, you start off by integrating and you use the plus C. Then, at this point, for all of these below, you're going to plug in the 310. You're going to plug in x as 3, and in this case, y as 10. Same in this problem. X equals 3, y equals 10, and you can figure out what C is. And then in this question, you're plugging in from f of 3 equals 10, you can pick out also, okay, that's the coordinate 3, 10, so still the same thing, x equals 3, y equals 10, plug it in, figure out what C is. And then what's left is what we call the particular solution, where you go back and say, oh, every single time the C was -2, I need to go back and fill in my formula with the C value being -2. I need to actually make sure I've found C and plugged it in. So a differential equation means you start with a derivative, and when they say solve this differential equation, it's expected that you understand that that means that you're supposed to find the original. So solving a differential equation means finding the original equation. If I give you f prime, I need you to find f. If I give you f double prime, I need you to find f. Okay? So actually, either kind of where you have your homework or on the back side where you've got some extra space, you might want to make a note. So like, oops, not with the highlighter. You start to see these on the second page of your assignment. And so like number 13 gives you f double prime of x equals 4x plus 5 e to the x. and they want you to solve that differential equation, well, you'd have to do it in a couple different steps. You'd first have to find f prime to backtrack just once, and f prime would be the integral of the 4x plus 5e to the x dx. And you would get 4x squared over 2 plus 5e to the x stays, and then you would have plus c for your f prime of x. Well, before you move on, you need to figure out what this c is, and if you read in the question, they should give you information about f prime to be able to find what c is. And they do. They tell you that f prime of 0 is 3. So plug in 3 for f prime, plug in 0 for x, and figure out what c is. Be really careful that just because you're plugging in 0, you don't assume that the whole right side goes away, because if you remember, anything to the 0 power, so like e to the 0 power, that's just 1. So this really becomes 3 equals 5 plus c, and you can keep going. Once you know c, you would fill in what f prime of x equals. Then you would integrate to find f of x. And you would do all your work, and you would end up with a plus c. And then you would plug in that coordinate to figure out that plus c for the final answer. Your final answer is the original function. Okay, so homework and notes and reminders. So 4-1 homework. I told you yesterday it's got funky numbering. I'm just going to go page by page. Page 1, numbers 1 and 11 are optional. Page 2, you also have a number 11. That is optional. Page 3, number 16, the F graph is optional. You must do the other graph that it's asking. Page 4, number 23 is optional. Page 5, numbers 17 and 18 are optional. And page 6, both number 26's are optional. And then 27B and D are optional. So you're getting this on Friday. First check off would be Monday, that hopefully you're done and you're just down to some questions. Then we would quiz and you would have your final check off on Tuesday of next week. Okay. Monday is a homeroom day, but my homeroom kids have a survey that we have to take. So help-wise, that's not going to work out too well. But Monday before school, if you need anything, you are welcome to come find me. And then we don't have a quiz until Tuesday, so Tuesday before school, you could come find me as well. All right. Thanks. Hopefully this goes well, and now you're starting to get some rules for how to find integrals or antiderivatives besides just area. If you have a formula, what you can do. All right.